Hello everyone, good afternoon. My name is Amalia Annur and I am going to present the final presentation of Nanomaterial for Energy Storage class entitled A Hydrogen Farm Strategy for Scalable Solar Hydrogen Production with Particulate Photocatalysis. And this paper originally is from Angewandte Chemie, which is a journal of the German Chemical Society, and it has an excellent impact factor of around 15,000 in the year of 2020, and still maintaining its leading position among scholarly journals with the focus on general chemistry. So the main topic of this paper is about one of the topic in our course, which is about photocatalytic overall water splitting process. So the photocatalytic overall water splitting using particulate photocatalyst is regarded as an economical and low investment cost and technical simplicity approach for large-scale hydrogen production. However, at present, photocatalytic overall water splitting still suffers from extremely low solar to hydrogen efficiency owing to the poor charge separation efficiency and the possible reverse reaction between hydrogen and oxygen. So author in this paper brings the concept of the natural photosynthesis to light, and there's the project is called Hydrogen Farm Project, or HFM, which there is an efficient capturing of solar energy in a large scale, and molecular oxygen evolves while supplying protons for the following energy storage step. So in the HFP, the water oxidation and proton reduction reaction are specially separated, consequently leaving out the hydrogen and oxygen gas separation. Based on this strategy, a scalable solar energy storage system can be operated using a photocatalysis dispersed in a reaction pool to capture solar energy through photocatalytic water oxidation. However, this HFP has some difficulties, such as highly active photocatalysis for efficient photocatalytic water oxidation, and also the suppressing the reverse action, which is the oxidation process of the reduced shuttle ions. So that's why in this work the author innovate to use the photocatalysis of bismuth vanadate as the photocatalysis as the bismuth vanadate has precisely tuning the 110 and 010 facets, which due to the tuning facets of bismuth vanadate, it will have an apparent quantum efficiency, or AKE, optimized, and also the reverse reaction of shuttle ions will be completely blocked. So next is the synthesis of tuning crystal facets of bismuth vanadate. So the bismuth nitrate, pentahydride, and ammonium vanadate will be mixed in a 2 molar of nitric acid solutions, and it will be stirred until complete solutions. And the 4 parallel solutions is made by making the pH condition of 0.25, 0.5, 0.75, and 1, and we then moved to hydrothermally treated for 24 hours. And then we centrifuge and dried overnight to obtain the tuning crystal facets of bismuth vanadate photocatalysis. The author also used the characterization of SRT UV-vis, SEM, HR, TEM, Raman, and KPFM, and used Venantorelli method to analyze Fe2+ and the evaluation of photocatalytic performance using both evacuation system and Clark-type oxygen electrode. This is the measurement of AKE using these equations, and also the author also used the produced Fe2+ solution, and using the produced Fe2+ to test its photoelectrochemical hydrogen production and electrolytic hydrogen production. So next is the result and discussion. So from the SEM result, we know that the effect of pH condition of the bismuth vanadate morphology, it is shown that all the bismuth vanadate crystal exhibit similar decahedral morphology, exposing 2 kinds of facets, 010 and 110, and it is successfully synthesized. And from the figure below, we can see that all the crystal facets has a special charge separation, while the reduction of AuCl4- ions here to Iu nanoparticles are all takes place on the 010 facets. Meanwhile, the photooxidation of Mn2+ ions to MnO X all takes place on the 110 facets. So it's all proven that spatial charge separation between 010 and 110 facets of bismuth vanadium crystal can be well maintained when changing the ratios of the facets. Next is SRD, Raman, and GVFIS. So from all the results, we can see that all bismuth vanadium photocatalysis in all pH conditions exhibits monoclinic morphology with all similar band gap of all samples, which is 2.31 electron volt. So next is to know the chemical potential of the redox shuttle ions, because it will determine how much solar energy can be stored in the HFP. So Fe3 plus Fe2 plus is an environmentally friendly and low-cost shuttle ions with a redox potential of 0.77 volt. It can be seen that the photocatalytic activities of bismuth vanadium crystals are closely correlated to the ratio of 110 and 010 surface area, which determines the reaction kinetics of Fe3 plus reduction and water oxidation reactions. And the optimized ratio is about 3.0, which indicates that the kinetics of reduction reaction is faster than that of the water oxidation reactions. The graph on the right hand side shows the CV curve that proves the reduction potential value is inconsistent with its redox potential, which is around 0.75. And from the Motsotsky plots, we can draw the energy diagram, and it shows that the conduction band levels is 0.59 volt, higher than the reduction potential, which is thermodynamically feasible for the reduction of Fe3 plus to Fe2 plus. Next is to know how much the separated holes participating in the water oxidation, the apparent quantum efficiencies or AQE of the bismuth vanadium crystal for photocatalytic water oxidation were evaluated. And the figure from the left hand side shows the AQE under different wavelengths of incident lights, and its AQE reached 71% at 365 nanometer and 62% at 420 nanometer. And its highest among AQEs reported for photocatalytic water oxidation on bismuth vanadium. Also, the solar to chemical energy conversion efficiency or STC is calculated to be 1.97% according to the measured AQE under different wavelengths. Talking about reverse reaction blocking, the main principle in the HFP is Fe3 plus ions are reduced to Fe2 plus with the photogenerated electrons, while H2O molecules are oxidized to oxygen. However, Fe2 plus ions will be still existing in the solution together with the Fe3 plus as the reaction proceeds, which can be easily oxidized back by the photogenerated holes, and it will cause losing of stored solar energy in HFP. But by seeing the time course of photocatalytic water oxidation using bismuth vanadium crystals, we found that the amount of photocatalytic oxygen evolution reached the theoretical value according to the added amount of Fe3 plus ions, and almost 100% of Fe3 plus ions were reduced to Fe2 plus. But this good result doesn't show as good in the irregular facets of bismuth vanadium. This graph suggests that the reverse reaction of Fe2 plus ions is totally blocked due to the significant role of the co-exposing 010 and 110 facets as the prohibiting the reverse reaction. To gain insight into the relation between the co-exposing 010 and 110 facets and the reaction selectivity on the bismuth vanadium crystal, several experiments were conducted, such as Kelvin probe force microscopy or KPFM characterizations, to differentiate the charge distribution on the different exposed facets. So first, the 010 facets pose more negative surface potential than the 110 facets, and the photogenerated electrons and holes are spatially separated between all the two facets, while the 010 facets are accumulated with photogenerated electrons, and 110 facets prefer to accumulate the photogenerated holes. And from the absorption of Fe3 plus under dark and light irradiation, so in the underdark, Some ferric species will be formed on 1,1,O facets due to the slight hydrolysis of ferric ions, but upon light irradiation, the majority of ferric species are formed on the O1O facets, so the light will enable to induce Fe3 plus ions to approach the O1O facets of bismuth vanadate crystals. And from all the SEM image and the UV vis spectra, it is proven that there is no iron species found in the surface after photocatalysis experiment, and it explains that there is no obvious hydrolysis reaction during the photocatalysis condition. All these phenomena may be due to the isoelectric point of the bismuth vanadate crystal, which is 3.3 below the photocatalytic condition at pH, which is 2.6. So when the photocatalysis occurs, the surface will be positively charged, so Fe3 plus are difficult to approach the 1,1,O facet due to the column repulsion interaction. Meanwhile, while the Fe2 plus generated from the Fe3 plus reduction process, Fe2 plus is also difficult to be accessible to 1,1,O due to the column repulsion interaction. Therefore, the forward reaction is smoothly facilitated, while the reverse reaction of Fe2 plus ions is also blocked. And this is the overall hydrolysis mechanism of the bismuth vanadate crystal PSF. So thank you very much. That's all my presentation today.